So just to jog our memory, let's go back to example 1 here. Let's look at the elevator question. So again, Alicia, it said this: a 72 kilogram man stands on a Newton scale in an elevator. By the way, the reason I said that is technically what units do scales measure in? Kilograms. But I want it in newtons. Who remembers, how do I go from newtons to kilograms? Divide by 9.8, because F equals m. If I want to get the m by itself, it's divide by the a. If I want to go from kilograms to newtons, it's times by 9.8. Heck, if you're in a rush and you're doing the math in your head, times by 10 or divide by 10. If you're standing in line at an amusement park ride and you want to figure this stuff out, and who wouldn't want to figure this stuff out while you're standing in line at an amusement park ride? I just times by 10 or divide by 10. Of course I do. So, what does the scale read? Oh, Alicia, what did I say when I'm talking about a scale? Which force am I really asking you to find? Normally. No? Okay. Accelerating upwards. What does the scale read? So it wants us to find the normal force. You know what? What's this a job for? A free body diagram. There's the person. Wow, suddenly the whole page changed. Let's try that again. There's the person. There's the person. Rebecca, what are the forces acting on this person? Get the obvious one. Absolutely, mg down. Is there a force up? The way I know there isn't a force up is if there was, that there is a force up. If there wasn't, it would be 9.8 meters per second squared down. Did I say that that was one of those numbers that was worth memorizing? I think I did way back, because you're going to use it so often. Okay. Which way is this person accelerating? I'm going to ask you the same question. I'm just going to phrase it differently. Which way will I have a bigger force drawn? Which way is the winner? Now, which force is that? Yeah, I know it's the scale pushing him up, but what does the scale measure? The normal force. So let's just bypass that. Let's call it the normal force. Rebecca, who's winning? Who's losing? So my equation, winner, take away loser, and that equals the net force, which is always ma. I think I told you guys when I first showed you the tug of war that eventually we'd reach the point where we didn't bother writing the word winner minus loser equals F net. We'd go straight to plugging the stuff in. What am I trying to find here? How would I get that by itself? Yeah. You can, I guess, if you really want to, memorize this equation. You know what? Memorize how to do a free body diagram in winner minus loser, and Ryan, whatever forces I throw at you, you can derive the equation in like 2 seconds. You said add the mg over. I agree. So it's going to be normal force equals ma plus mg. So here's my question. When an elevator is accelerating upwards, or when the elevator is accelerating upwards, do you feel heavier or lighter? How do you know? Convince me. Well, it's what I felt. What do you feel as your normal force right now at this moment? In fact, what do you feel, no pun intended, normally as your normal force? Mg. Rebecca, what did we get? Mg what? Plus. Oh, if we're adding, you're going to feel a bigger normal force. You're going to feel heavier. Which, if you're ever on the elevator, or if you're in an express elevator, because most elevators have a really wimpy acceleration, and you really have to concentrate to notice that you do feel heavier. Oh, and it's only while it's accelerating. Once it hits a constant speed, which most elevators get to pretty quick, you're not going to notice anything anymore, because now you'll feel a normal force. Boy, that's awkward to say. Anyways, you will feel heavier. Okay? Mass was 72. A was 2.5. Plus 72 times 9.8. 72, can I do this in my head? It's going to be 72 times 12.3. Nah, yucky math. Let's just crunch it. $72 times 2.5 plus 72 times 9.8. You get 885.6. I'll call that 886. And it's a force newtons. D. accelerating downwards at 3.2 meters per second squared. John, what do they want me to find here? You know what this is a job for? I think so. John, what are the forces acting on this person? Get the obvious one. What else? Okay, so what other forces are acting on this person? Because acceleration isn't a force. Which way? I think the normal force is going to point up. Now here's the question. Am I going to draw the normal force bigger, smaller, or the same size as gravity? I think that's what you were trying to get across. And I think first thing in the morning, your brain is still, have a little more coffee. Hey, what's my equation going to be, John? By the way, you'll notice I'm giving you less and less hints along the way. Sorry, but I used to walk you through everything. Now I'm just, what's next? Winner minus loser equals MA. What did you say I'm trying to get by itself? How? How? Okay. Stay off your phone. Thank you. And? Oh, so if I hear you correctly, and I think I do, you're telling me the little mg would just drop down like a domino? There would be a minus ma, and that's your normal force? Question for you, John. On the way down, would you feel heavier or lighter? Convince me. What do you normally feel for the normal force? No pun intended. More specific. What do you all, right now, what are you feeling as your normal force? How hard do you feel the chair pushing up? mg, right there. Oh, are we subtracting something from mg? So has the normal force gotten smaller than what we're normally used to? We would feel that as, lighter. Okay? And I think I said last day, that's the one that gets our attention the most. All of you have experienced an increasing normal force. The bottom of a swing set, for example. Someone, was it this class or one of my other classes, said, hey, Mr. Duke, what about at the top of the swing? Do we feel lighter? And you know what? I got to draw a good free body diagram and visualize whether you're feeling lighter or whether you're feeling exactly mg at the top of the swing. I'll do that sometime. But anyways, hey, now it's plug and chug. The normal force is going to be 72 times 9.8. John, why don't I need to put a negative 9.8 in here? I took care of it where? With that arrow. That arrow has the negative and takes care of my signs for me. This is one time Courtney, who's going to now open her eyes and stay awake. This is one time it was nicer to let down be positive. The math just works out prettier. Minus 72 times 3.72. You going to make it, Court? Because that was a long blank. And yay, I'll call it 438 newtons. Have I said I like this question? I like this question. You know what? It's going to be an elevator. Although I think I've just decided to make it more interesting. We'll make it the elevator ride at Playland. Have I told you all how those rides were invented? Put your pencils down. Pause the video for 1 second. Air resistance. This is where we left off. What's air resistance? Air resistance is the force of air molecules bumping into an object that's moving through the air. Because air has mass. You've all felt it when you were biking or running or putting your hand out the window of a car. Turns out, in fact, air resistance can be quite large. I've told you, but I'll repeat myself, Ryan, air resistance is very, very tough to calculate. In fact, I showed my other physics block the equation, and I'll walk you through it another time if you guys want to. It's difficult. So, but this is where we paused. Here's the key. If you want to underline anything, the force of air resistance has direction opposite to motion. If the object is moving left, which way is air resistance? Right. If the object is moving up, which way is air resistance? Down. If the object is moving down, which way is air resistance? So it says, draw force diagrams for each of the following. a ball being thrown, a rising ball, and we're going to include air resistance, and a falling ball, and we're going to include air resistance. Alex, what we're talking about is the ball being thrown, this part, before it leaves my hand. Part B is right there on the way up, so right here. Part C is right here, but on the way down. Is that okay? So, what are the forces acting on this ball? Get the obvious one. You know what? Let's just put a dot right in the middle of the ball. That'll work. What are the forces acting on this ball? Get the obvious one. Gravity. Right now, which way is the ball accelerating? So there must be a bigger force pointing which way? Up. By the way, watch. I will move the ball up, but I won't give it a bigger force than gravity. Won't leave my hand down. I have to make sure that the force is larger than mg. Otherwise, it's not going to have a net force pointing up. It won't accelerate up. So I can move it up, no problem. But I have to make sure that the net acceleration is up. I have to make sure that my hand force, in fact, let's call it F hand. You could argue that it's sort of like a normal force or whatever, but just to make it really clear, I'm going to say F hand. And if F hand isn't bigger than mg, the ball won't leave your hand. I'm also going to ignore air resistance during the throw. I'm going to pretend that I'm throwing it like this. I don't know. Just keep the physics nice. It leaves my hand. It's on the way up. What are the forces acting on it? Get the obvious one. Really, people? Get the obvious one. Yes. Which way? What else? Air resistance. Which way? How do you know? Because air resistance always acts opposite to the direction of motion. So the ball moving up. Usually if there's two forces in the same direction, I'll just draw another arrow a little bit beside, and I'll call that F air or F drag or something like that. What about when it's on its way down? What are the forces acting on it? Get gravity. What else? Which way? Bigger, smaller, or the same size as gravity? Well, right at the beginning, smaller. If you hit terminal velocity, like when I jumped out of an airplane, eventually I jumped out of an airplane, then it's the same size. And it can be bigger. When I open my parachute for a split second, it's bigger. That's what slows me down. I need to have a net acceleration up. But for now, let's do that. But this comes to something that bugs people. In example 4b, that's this one right here. How can the ball be moving up when all the forces on it are acting down? I would argue it was never accelerating up. But I'm talking about situation B, Chief. This is hugely important, and maybe it's so obvious that it's not obvious. There is a difference between velocity and acceleration. Velocity and acceleration do not have to be in the same direction. In fact, often they're not. As an example, when you hit the brakes in your car, which way is your car still moving? Forwards. But which way are you accelerating when you hit the brakes? Backwards. And this is important, Alex, because students, especially non-physics people, they want velocity and acceleration to be the same thing or the same direction. Because, by the way, it's easy to get them mixed up because one's meters per second, one's meters per second squared. This is why I spent so much time before Christmas trying to make sure you could help differentiate between the two. So, explain using relevant physics principles. I would just say this. Velocity, acceleration don't have to be in the same direction. Now, if you accelerate for a long time, eventually your acceleration and your velocity will end up being in the same direction. In other words, ready, Connor? which way is ball B traveling? Which direction is its velocity? I'm looking for a word that begins with the letter U. Which way is it accelerating? Down. And eventually it will end up with a velocity that's moving down too. Part C. Eventually. But it doesn't have to be that way. It doesn't have to start that way. Is that okay? Example 6, if the falling ball in 4C is speeding up, write a net force equation. I had to add that because I've given you a little secret then. If it's speeding up, which way is it accelerating? Who's winning? That's why I had to say that. Could have been a tie, then that would be terminal velocity. Could have been bigger, like when I opened my parachute. But here, Prith, what's the equation? Who's winning? Who's losing? What does that always equal? Yeah, there's a net force equation. And if I knew the acceleration and I knew the mass, I could calculate air resistance. Or if I told you air resistance, you could find the acceleration or whatever. Point being, don't memorize that equation. Courtney, what I'm saying is if you can draw a free body diagram and then use winner minus loser, you can derive whatever equation you need for the situation that we're at. That's been my rant for the past couple of days. Okay. Example 7, a 90 kilo, you know what? Me. Let's suppose I'm the parachutist. I jumped out of an airplane, imagine I jumped out of an airplane, and I free fall for a while, and then I open a parachute. My new upwards acceleration is 1.5 meters per second squared because I'm slowing down, even though I have a downwards velocity. If my velocity is downwards and I'm slowing down, which way must I be accelerating? Upwards. Okay? Draw a free body diagram. What are the forces acting on me when I was in free fall? Get the obvious one. Yep. What else? Air resistance, bigger, smaller, or the same size as gravity? Right now, at this moment in time, bigger, smaller, or the same size? Bigger. And the reason I said right now at this moment in time is air resistance changes depending on how fast you're traveling. And if I'm slowing down, air resistance is going to get smaller. But for now, we have that. You can call it air resistance or drag or whatever. A says draw a free body diagram. There. A. B says write a force equation. Andy, what's my force equation? No, I want the whole thing. It's going to equal MA. I got to be fussy. You said F minus mg. I don't see an F on my free body diagram. What? Let's be specific, okay? Because, by the way, everything is an F technically because everything is a force, so let's be specific. F air. If I hear you correctly, Andy, and I think you went winner minus loser, and you said, oh, I know air must be winning because that's which way we're accelerating. Okay. Andy, what does part C want me to find? Oh, let's get the air resistance by itself. You should have seen his face. He kind of looked at me and went, well, just plus the mg over, Captain Obvious. I love that you've come that far because at the beginning of the year that might have seemed abstract and terrifying. If I've done my job right with formula manipulation, if it's becoming boring and obvious, I say, wahoo, that was my goal. Rather than memorize a bunch of crap. If I can get you at the point where you just see the different equations, that's a nice stage to be at, my friend. So if I heard you correctly, you're telling me in other words, Andy, right at that moment in my harness, I felt heavier. You know how I know? Because normally I would have felt dangling from my harness mg. And right then, dangling from the harness, I felt... Anyways. Because if you draw a free body diagram of me and the harness, it turns out what I'm feeling is air resist. Anyway. Did they give me the mass? 90 times 9.8 plus 90. They gave me the acceleration, 1.5. I don't need to worry about which one was positive, which one was negative. I took care of that, Haley, with my arrows in my diagram, and I'm going winner minus loser. It's plug and chug. You know what? I might be able to do this in my head. It's going to be 10 point. It's going to be 11.3. 90 times 11.3. Yeah, I can do this in my head. 90 times 11.3. It's going to be 909. 1,024. No, I'm off. 90 times 9.8 plus 90 times 1.5. 1,017. I said 1,024. Yeah. Oh, geez, do it. 1,017. You know what? Let's go to 3 sig figs. How about 1,020 newtons? And then I was technically right. What's my point? What's my rant, Trevor? A good free body diagram, you can derive whatever you need. By the way, the other thing I could have done, Trevor, I could have given you the air resistance and said, find the acceleration. How would I get the A by itself? More specific. Yeah. Those are the big two. It's going to be either find an unknown force, or I'll tell you the unknown force and I'll say, find the acceleration. Eventually, I'll also give you this, this, and this and say, find the mass. But how many m's do you see in this equation? 2. We're going to have to learn to deal with that. That's coming, preview of coming attractions down the pipe. But that's another thing we can find. The force of air resistance is actually not a constant value. In fact, the force gets larger as speed increases. A falling object will eventually reach the point where the force, typo, of air resistance equals the weight of the object. At this point, it will hold a steady speed, which we call terminal velocity. I have a video, and I think, put your pencils down. So, in fact, this is the last question. Yeah. A parachutist jumps out of an airplane. I mentioned I jumped out of an airplane, and free falls. They reach terminal speed, and they maintain that speed for a while. They then open their parachute. They quickly reach a different terminal speed and descend to the ground. By the way, the reason I said terminal speed and not terminal velocities, what direction was my velocity when I jumped out of an airplane? Down, which would be negative, and I don't want to draw a negative graph. So we're just going to look at the speed. How big? Okay. Sketch a speed versus time graph. Okay. Here's our graph. Speed versus time. And really, Alicia, we're talking vertical speed. All right. I'm sitting in the plane. I've got my legs out the door, but I'm just sitting there. I haven't jumped yet. What's my vertical speed? It's meant to be really obvious. 0. So draw a little line. This would be me sitting on the edge of the door working up my nerve. I don't know how much time elapses, but sometime. I jump. Ah! What's going to happen to my speed? It's going to increase. Now, let's include air resistance. I think it's going to increase most rapidly at the beginning. And as air resistance gets bigger, it's not going to increase as fast. I think, Matt, it'll look like this. And it'll plateau, and that horizontal section there, that's terminal velocity. For those of you in Math 11, it may very well, this section right here might even be a parabola. I'd have to go double check the equation. I think it does have a square in it. Okay, I free fall at terminal velocity. Then I pull my parachute. What happens to my speed? Decreases. Does it decrease faster at the beginning or faster at the end? I think it, like that. It decreases really fast at the beginning, and it decreases slower at the end, and I hit a new terminal velocity. Now, Lydia, the only problem with this is my time scale is garbage. Really, I was drifting down for 5 minutes, and I was in free fall for about 30 seconds, but I don't want to draw a graph that goes all the way off your page, so can we just agree that my shape, Alex, is going to be right, the shape of the graph is going to be right, but it should be stretched out more. Is that okay? Then I drift to the ground. When I get to the ground, what's my new speed? And you know what? Drift, 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 and I'd hit the ground pretty quick. Probably like that. Sort of looks like the side of an old VW car almost. I don't know. Is that okay? Jess, you good with that? I think that's from, and that's also, I wanted to do a little bit of review. Remember all the graphs we did before Christmas? This is a nice way to get us thinking both as a picture and as a free body diagram. What's your, I think this is it, yes? Video we already watched. Yeah, what's your homework? So finish this off, and then I assigned number 1 and number 2 and number 3 last class. Number 4, I can now add number 5, because that's air resistance. I can add number 6, number 7, number 8, number 9. So I think that's all of them, isn't it? And your first priority is finish the take-home quiz. I said I wanted to give you 30 minutes. I'm giving you 32 minutes and 15 seconds. Oh, don't thank me. Even extra time.